Yet again, hello lovely grade 12s, and today we are going to be discussing tangent to a curve. So this is just a continuation on all of the video clips about derivatives and differential calculus, and this topic specifically today refers to if I have a curve and I want to work out the equation of a tangent to said curve. Now, first thing we need to talk about is we need to talk about what a tangent to a curve is. So pretty much a tangent to a curve says if I have any type of curve, and that could be a parabola, just a small section of a parabola, that could even be a small section of an exponential graph, any of the functions that you know in algebra. So those functions that give me a curve, I can then go and I can identify a point. And I've specifically said this point that I've identified is a random point A. It could have been 2, it could have been 1, it could have been 3. It's got to be a point on the graph of f. So I've identified that random point A, and I've said because A is an x coordinate and it's a point on the graph of f, the corresponding y coordinate is going to be the f of A, which by now, hopefully after all the substitutions we've done in first principles differentiation, means you understand that this just reflects the y coordinate of that point. And then if I now go and I draw a line, and very important, that line that I draw has got to have a point of contact. And when I say a point of contact, it can't go and cut through two different points. Because the moment it cuts through two different points, referring back to the video on average gradient, we are looking at the average gradient between 2 points. Whereas if I draw a tangent, so a line that only has one point of contact with a graph, then this is not an average gradient. This is what we refer to as an instantaneous gradient. So that line that I draw over there is a tangent to the curve of f at x equal to a. Now, just to show you on GeoGebra again, I'm going to make this slightly smaller so you can see it a little bit better. Okay, so if I go, for instance, and in this case, I've drawn a parabola. So I draw a parabola, and I've picked a point right there on the parabola. In this case, it could be any random point. And then what I do is you'll see right here, there is my tangent. So that tangent only has the one point of contact at that point A. Then you should notice if I go and I move this particular point right there. Sorry, that was technical difficulties again. Let's just do that. So if I take that point A and I then go and I drag that point, you should notice that as the point changes, so as the point of contact changes, the line changes. So that tangent will have a different gradient, will have a different y-intercept over here, depending on where that point of contact is. So it's very important to realize that we are going to calculate the equation of a tangent, but that equation of the tangent is dependent not only on the curve, but it's also dependent on the point of contact, because the point of contact determines what is the gradient of that line and also what's going to be the y-intercept of that line. So very important when we get there later. Okay, so here we go. We've now established a tangent is a straight line. So all straight lines are written in the form y is equal to mx plus c. And you need to be very aware of this. The gradient of the tangent is the same as the gradient of the curve at that point of contact. So if I bring back my iPad again and I just look at this, this is the part that you need to notice. The gradient of the curve, and you'll see it's got a changing gradient, that curve. So over there, the gradient is negative, and then over there, the gradient is positive. But the gradient of that tangent, that straight line, is exactly the same as the gradient of the tangent at that particular point of contact. So that's why if I change the point of contact, I change the gradient of the tangent, because at that point of contact, the graph has differing gradients. And remember, again, I want to reiterate, I say derivatives, you say gradients. We are all busy with gradients. This entire section is just about gradients. Now, again, please remember, please remember the following. If I then go and I draw a tangent at a particular point in contact, then that point of contact needs to have an x coordinate, which I've now said a random point A in this case, And then if I sub that x coordinate into the function, it's going to give me my y coordinate. But as I've just stated up here, the gradient of the tangent is the same as the gradient of the curve at the point of contact. So that means the gradient of the tangent is going to be equal to the first derivative. Also, I'm now sometimes going to refer to that first derivative as the gradient function. So the first derivative where that point of contact is made. So I know normally we write f accent of x, but that's called the gradient function. Whereas if I have an actual x coordinate, I can sub that x coordinate into that gradient function and I will get a value. I will get a gradient, and that gradient is then the gradient of the tangent where x is equal to a. So please remember that when we do these examples on the tangent to a curve, you have to remember that idea that if I want to get the gradient of the tangent, it's going to be subbing the x coordinate into the first derivative. That will give me the gradient of the tangent. Okay, so let's look at our first example. Now again, we are going to follow the Luzandi method here. I am going to give this to you step by step by step. So the way I've set it up, I've given you an example which we'll do step by step by step, and then the next example we will just flow through the example without first getting stuck on all of the steps. So how to find the equation of a tangent to a graph. And this example is example 1 on page 206 in the textbook. Find the equation of the tangent to the graph of f, and they define the graph of f as minus x squared plus 2x plus 3 at x equal to 2. Now this, by the way, is a parabola because it's a quadratic graph, and it's got a shape which has got that negative a value. So the negative a value means it's going to look like this. Now no, people, you don't have to draw that, but just now, after we found the entire tangent, after we've done all the steps and we've come and found the equation of the tangent, I'm going to refer back to this just to give you an idea, a better picture of what it is that we're actually trying to do. So here are the steps. Step 1. The moment you see the word tangent, you realize tangents have to do with gradients. And because tangents have to do with gradients, step 1, determine the first derivative. So whatever they defined as fx, I'm going to go and determine the first derivative of that given fx. So in this particular example, I'm going to go and say the first derivative is then equal to 2 times negative 1, which is negative 2, x to the power of 2 minus 1, because remember we're making that exponent 1 less, so there's a little 1 there, plus, and then the derivative of 2x, we've already said, is just going to be 2. But again, if you're wondering why is it 2, there's a little 1 over there, so I'm multiplying 1 by 2, and then I take the exponent and I always make that exponent 1 less. So 1 minus 1 is 0 and x to the power of 0 is 1. And then also remember the derivative of a constant is equal to 0. So now we've got that first derivative, and we're going to use that in step 2 to calculate the gradient of the tangent. So we're going to say step 2, determine the gradient of the tangent by subbing the x coordinate into the first derivative function. Because remember, I'm going to start talking about that first derivative now. I'm going to be calling it the gradient function. So any x value subbed into this particular function, the first derivative, is going to give you the gradient. Now, please note, they've given you the point of contact as x equal to 2. So that's the x coordinate that I'm going to be subbing into the derivative. So the gradient of the tangent, where x is equal to 2, is the first derivative where x is equal to 2. So I can then just sub that 2 into my first derivative, saying it's minus 2 times 2 plus 2. And that's going to give me minus 4 plus 2, so it's minus 2. And that, people, is the gradient of my tangent. Now I'm almost done, because step 3 means I need to now find the y coordinate of the point of contact. So I'm going to say determine the y coordinate of that point of contact by subbing the x coordinate. Very important, do not get confused. I have to sub the x coordinate into fx. Because now we're going to have fx, which is the function, and we're going to have the derivative of fx, which is the gradient function. So very, very important, if I sub x coordinates into fx, what I get out is the corresponding y coordinate. But if I sub x coordinates into the derivative of fx, what I get out are gradients. So please remember, guys, subbing into fx gives me a y coordinate, subbing into the first derivative of fx gives me the gradient. So I'm going to sub that 2, which is the x coordinate of the point of contact, into the original function fx. So it's minus 2 squared plus 2 times 2 plus 3, which was the original function defined up over there. Right, so calculating this, it gives me minus 4 plus 3, which means my y coordinate is then 3. Now I've got everything I need to find the equation of this particular tangent. So step 4 is going to be sub all the information into that formula, which is an analytical geometry formula. And if you recall, it's that analytical geometry formula, y minus y1 is equal to m times x minus x1. If you're not comfortable with using this formula, you could use the formula y is equal to mx plus c. Just recognizing that we have everything we need. We have the x coordinate of the point of contact, which is 2. We have the y coordinate of the point of contact, which is 3. So the point 2, 3 is a point on this tangent. And then I also have the gradient of the tangent there, which is negative 2. So subbing into this, I'm going to say y minus 3 is equal to the tangent gradient, which is negative 2, times x minus 2. And I will just simplify this, and that will give me y is equal to minus 2x, and that's going to be plus 4 plus 3, so it's plus 7. So right there, this is the equation of my tangent. And this is pretty much in 4 steps how to calculate the equation of a tangent if the point of contact is given. So we're going to do another example on this, and the next example will flow much, much more easily because I'm not going to get stuck on every single steps, but these are the steps I'm going to follow in the next example as well. Right, so this particular example is from the Department of Basic Education. It was their November 2019 paper 1, and it gave you the curve with equation y is equal to x plus 12 over x passes through the point A, and A has got the x coordinate of 2. They don't tell me what the y coordinate is, but we now saw in the previous example, if I want a y coordinate, I just have to sub the x coordinate into the original function. I mean, it's even telling me over there, if you want the y coordinate, sub it in there, and that will give you the y coordinate. Determine the equation of the line, and now careful with this one, because this one says of the line perpendicular to the tangent at A. So this one's slightly trickier, because it doesn't ask you for the tangent. It asks you for the line perpendicular to the tangent. And we will talk about that just now. But first we'll follow the exact same steps that I followed just now. So we're going to start off by saying I need to find the first derivative of that function. And now you'll see we need to prep the algebra a little bit. We need to go and first say y is equal to x plus 12x to the power of negative 1, because I can't find the first derivative if I have an x in the denominator, so I first had to prep it. So that's y. And now I can find the first derivative using my notation dy over dx, which is going to be equal to 1, because the derivative of x is 1, minus 12x to the power of negative 2, just using my differentiation laws. Now I need to go and I need to sub 2 into this to get the gradient of the tangent. So the gradient of the tangent is then going to be equal to 1 minus 12 times 2 to the power of negative 2. Now yes, you can type that into your calculator. I'm just going to go and work it out by saying 1 minus 12 over 4. And please remember, it's 12 over 4 because it's 2 to the power of 2, which is 4, but it's 2 to the power of negative 2. So that means it's over 4. So I've got 1 minus 3, which means this is equal to negative 2. Now that negative 2, as I wrote over here, is the gradient of the tangent. And now this is the only place it deviates from those steps that I showed you. It doesn't want the equation of the tangent. It wants the equation of the line perpendicular to the tangent at A. Now, all I need to remember is perpendicular lines, and I'll write it up over here, has got a product. So if I go and I say one line with a gradient of 1, so the first line, times the gradient of another line is equal to -1 if the lines are perpendicular. Or like I told my kids, which you might not know, but if you have two lines that are perpendicular and you've got their gradients, then the gradient of the one line is going to be equal to -1 over the gradient of the other line. So you can actually just go and say, if you want to find the gradient of a perpendicular line and you have the one gradient, you just change the sign and you write the reciprocal down. So that's pretty much what I'm going to use down here. So I'm going to use down here that if the gradient of the tangent is -2, then it means the gradient of the perpendicular line is going to be equal to, change the sign, so the negative becomes positive, and then write the reciprocal of 2, which is going to be a half. Because obviously, -2 times a half gives me that -1, which means these two gradients are the gradients of perpendicular lines. And this is what I'm going to use in the next step. I'm not going to use the -2 because I don't want the equation of a tangent. I want the equation of a line perpendicular to the tangent. Then, still going ahead with the steps, we now need to go and we need to work out the y-coordinate of that point of contact. So they told me the point of contact is the point 2b. So I'm actually going to substitute 2 into x in the original equation, and I'm going to substitute b into y in the original equation. So I'm going to say b is now equal to 2 plus 12 over 2. And that's going to be 2 plus 6, which gives me 8. So that pretty much just means that A is the point 28. And that point 28 is my point of contact. So again, I've got the gradient of the line perpendicular to the curve or the tangent, and then I've got the point of contact, which is a point on that particular line. And I can then just, in the last step, sub it in saying y minus 8 is then equal to a half times x minus 2. And simplifying that, I've got y is equal to half x, and then a half times -2 is -1, so -1 plus 8 gives me plus 7. So yes, this one had a little trick. I couldn't use that gradient as is because they didn't ask for the equation of a tangent. They asked for the equation of a line perpendicular. So that was a little side note over there, but pretty much it follows those steps that I showed you in the previous example. Now, they can obviously go and change it up. And this isn't really a Josh method. So Josh, sorry, no, this is not as complicated as it can get. It can get more complicated than this. But there are other examples, and specifically these examples, what they do is instead of giving you the point of contact, they give you the gradient. So let's read through the example and then talk about it. And I will again with these ones write down step by step what needs to be done. And then I will, in the next example, I'll do it much more easily. I'll make sure that it flows a little bit easier. Okay, so in this one it says, find the equation of the tangent to f, and fx is defined as x cubed plus 1. But now, instead of saying where the tangent makes contact, in other words, the point of contact, it says parallel to the line gx is equal to 3x plus 2. So because we have the following words, specifically parallel, there we go, there's parallel, very important, to that line gx is equal to 3. We know that parallel lines have the same gradient. So if my tangent is parallel to that particular line, then I know that the gradient of that tangent, very important from here, the gradient of the tangent is going to be equal to 3. So please don't forget this. I'm going to put it in there just now, but parallel lines have the same gradient. So if they tell me the tangent is parallel to that line, it's got to have that gradient of 3. So to do these ones, step 1. Now the good news is step 1 is still determine the first derivative because we're working with gradients, and gradients require us to work out first derivative. So determine the first derivative. And I'll go back to this function saying the first derivative of that function is then equal to 3 times x, and then I make the exponent 1 less, which means it's 2. And then the derivative of 1, which is a constant, is just 0. So that's the first step. Then step 2 is different. And the reason step 2 is different is in the previous example, we had to go and we had to substitute the given x coordinate into that first derivative to get the gradient. This one is going the other route. In other words, we don't have the point of contact, but we do have the gradient. And that is why I'm going to say set that first derivative of fx equal to the gradient of the tangent. So whatever gradient they gave you, we're going to set these two equal. Now, the logic behind this is very simple and straightforward to understand. The derivative is the gradient. The gradient is the derivative. So if I know the gradient function is 3x squared, and I know the gradient is 3, this gives me an equation that I can solve to find x. And what is x? X is the point of contact. So if I solve this, I'm going to divide both sides by 3, which gives me x squared is equal to 1. And then I'm going to use the square root, but please people, I say this to my guys again and again and again. If you use a square root, don't forget the plus minus, because this is a quadratic equation and it needs two answers. The plus minus gives me the two answers. So x is equal to plus or minus the square root of 1, which is 1. Now, you look at the two answers and you go like, that's a little bit strange. Not necessarily. And the reason this is not necessarily all that strange has to do with the fact that up here they actually told me find the equation of the tangent right there. So find the equation not of the tangent, it could potentially be more than one tangent. So find the equation of the tangents. And this is why the moment you find those two x coordinates, you suddenly realize that, oh, this is why they asked for the equation of the tangents, because if I have 2 points of contact, that means in this particular curve, there are 2 places where I have that gradient of 3. Now, not that you know this yet, we'll get to this later when we get to cubic graphs, but the graph that was given, the function of f that was given up here, just for interest's sake, that graph looks like this. And because the graph looks like that, over here there might be a gradient of 3, so that could be a gradient of 3, but over here you will see there as well there could potentially be a gradient of 3. So that's why over here, and I'm just going to put this in a bubble so it's separate, that's why it's quite possible that one single graph could have 2 tangents with the same gradient. And because they've got 2 tangents, I've got 2 points of contact. And this is why I ended up with 2 x coordinates for those 2 points of contact. So, step 3, luckily for us, is the same as the previous example, which is substitute the x coordinate into fx to get the y coordinate. And now we're just going to have to do that twice, because they're going to be 2 points, so they're going to be 2 y coordinates, so they're going to be 2 lines. So sub the x coordinate into fx to determine the y coordinate. So I'm going to have to go and say it's the f of -1, and I'm going to also have to say it's the f of +1. So -1 gives me -1 cubed plus 1, subbing it into the original function. Remember, if I want to get a y coordinate, it's got to go into the original function. Because if I go and I substitute this into the derivative, I'm just going to end up with 3, because that's going to give me the gradient, which I know is 3. So I sub it in there, and I end up with -1 plus 1, so that means my y coordinate over there is 0. So this point of contact is the point -1, 0. And then I sub 1 again into that original function, so 1 cubed plus 1, and that's going to be equal to 1 plus 1, which is 2. Which means the other point of contact is the point 1, 2. Now finishing that off, step 4 is just substitute all that information that I've now got into that straight line equation. And like I said, this appears on your formula sheet. It's part of your analytical geometry, and it's a very easy formula to use. But if you don't like to use it, you can use the y is equal to mx plus c. So we're going to start by saying the first one, y minus 0, because the y coordinate is 0, is equal to the gradient. And please people, don't go like, oh, but we never calculated the gradient. They gave me the gradient up here. The gradient of the tangent is 3. That's what I use to find the x coordinates. So I do have the gradient of the tangent. So it's 3 times x minus -1, so x plus 1. And if I simplify that, I get y is equal to 3x plus 3. So that's the first possible tangent. Now the second possible tangent is then going to be y minus 2. So y minus the y coordinate is equal to the gradient of that tangent, which is 3 times x minus 1. And then if I simplify that, I get y is equal to 3x minus 3 plus 2. So minus 3 plus 2 is minus 1. And those are the two tangents that I find if I know that the gradient is 3 up here. So this is just another way of asking tangents, where instead of giving the point of contact, they give you the gradient, and these are the steps that follow if you don't have the point of contact, but you do have the gradient. Now we have one last example to do. And this particular example, we're going to flow again, we're going to do it much faster. It's from the IEB March 2018, so the March 2018 Supplementary Paper 1, question 5D. And it said, given that fx is equal to x squared minus 3x minus 6, determine the equation of the tangent to f, which is perpendicular to the line gx is equal to half x plus 5. So again, this time they didn't tell us the lines are parallel, they told us the lines are perpendicular. And remember, perpendicular, the gradient is not the same. This, by the way, would have been the gradient to the tangent. Got it. But I don't want the gradient of the tangent because I want to have a line that's perpendicular. So the gradient I want, if you recall, we have to change the sign, so that's negative, and then we need to write the reciprocal down, so that's 2, because a half times negative 2 is negative 1. So I've now got the gradient of that line perpendicular. So first find the first derivative, because that is the gradient, which is 2x minus 3. Saying 2 times x and make the exponent 1 less, and that's 3. And again, please remember the derivative of a constant is 0. Now, I don't have a point of contact to sub into x, but I do know what my gradient is. And please remember, first derivatives are equal to gradients. They are the gradients. I keep on telling you guys, I say derivative, you say gradient. So you have to remember, first derivative is all about gradient. So I'm going to go and say, but the gradient is negative 2. So negative 2 is equal to 2x minus 3. And that allows me to now solve for the point of contact. So I'm going to say minus 2 plus 3 is 1, which means x is then equal to a half. So that is the x coordinate of my point of contact. I'm going to sub this, careful, into the original equation to get the y coordinate. So I'm going to say the y coordinate is then equal to the f of a half, which is equal to a half squared minus 3 times a half minus 6. And I'm going to be super lazy right now. I'm just going to let the calculator do the work. So, a half, whoops, technical difficulties today. A half squared minus 3 times a half minus 6. And that gives me a y coordinate of minus 29 over 4. So it's a good thing I use the calculator because this is just much easier. So a half squared minus 3 times a half minus 6 is minus 29 over 4. So that means the point of contact is the point a half minus 29 over 4. And then finally I can just sub that into my formula. So y minus negative 29 over 4, so y plus 29 over 4, is then equal to my gradient, which up here we got as negative 2, times x minus a half. And then just to finish that up, I'm again going to use the calculator to help me simplify. So that's going to be minus 2x, and I'm going to multiply minus 2 by a half, negative a half, which is 1. And then I'm going to subtract that 29 over 4, which gives me minus 25 over 4. And that's the equation of this particular tangent. Thank you for listening.